Yeah. Diganta will tie up some loose ends from his previous lecture, for about 20 minutes or half an hour. After that, I intend to take over to give you what I call as a gentle introduction to what formal verification is and how we go about, of which you saw some teasers in our Z3 class and the logic recap classes. By the way, January 30th, I didn't know. I mean, I thought originally it was announced that 24th was the registration deadline. But later I realized that it had been moved to January 30th. Which one is it? 30th January. Okay. So, yeah, I don't know how many of you have taken, have started working on the logic assignment. I would like all of you to work on it. And my intention was to have the deadline for that as January 30th, the course registration deadline. So you could continue to work on it. And there may be some problems there which require to understand what transition system is and so on. If you're unable to solve those problems, that's okay. Try to solve as many as you can for which you have already seen material covered in the logic class, and try to submit on January 30th. Okay. Uh, uh, yeah, with that, Diganta, you can start.
Okay, yeah. So I'll start sharing my screen. Yeah. Is my slide visible?
Yes.
Okay, sure. So last time we had, I had talked about the back propagation, and then I kind of wanted to motivate why we want to do formal analysis of neural networks, and I talked a bit about these adversarial attacks that can fool neural networks and how they seem to be neural networks seem to be very susceptible to it, no matter what you do. And there are techniques which are heuristic techniques, but they can also be fooled by adversarial attacks. So you might think from certain heuristics the neural network is doing something reasonable, but it turns out that actually you can perturb your inputs in such a way that that kind of throws that intuition off, right? So what we really need are formal guarantees and safety. Given that, I wanted to talk briefly about like how neural network verification works, like at a very high level brief overview. And I think this will tie in well with what one does generally in formal methods as well. So okay, so we have the DNN verification problem, right? So suppose that we have network N, and the way that we formulate this problem is in this particular way, where we sort of say that we'll have some condition which holds in the input and then expect some condition to hold in the output, right? So if you go back to some of the examples that I had talked about, so let's say that we have this top side, right? So let's say that my input condition somehow encodes that I have an image of a stop sign with some patches in unknown, like in locations that are not necessarily fixed, right? So let's say that I have this space of possible images where I start with a image of a stop sign and add a patch at some particular position, right? So that space of possible images can be described by some formula, and if this is kind of vague, we will concretize this later on in the course. But it can be described by some formula, and this can be saying something like, okay, at such and such pixel values, let's say that at such and such pixel values, you have either your stop sign pixel or maybe a patch pixel, right? So you can create elaborate formulas that kind of encode these kinds of properties, and then you can also create a formula that encodes what you want to be true at the output, right? So you can say that, okay, if this kind of formula holds the input, which basically means that I have some patch on the covering a part of my image, let's say, then I want some other kind of formula to hold in the output as well, right? And then this, the behavior of the network that I expect can then basically be written as this whole expression, right? So in some sense, if you want to, let's say that if my input has got a patch at any given position, I want the output classification to not change, right? So that whole thing I can write it as an expression. So this is saying the input has some kind of a patch, and then saying that, okay, y I get when I apply the network on my input image x, and then this expression can simply say that the classification of y is in fact the correct classification. It's still a stop sign, which is what we expect. And then therefore this whole expression is basically characterizing a property for the network that we want the network to hold, right? So then if that is the case, then this should we should be able to, in some sense, formal verification or the linear verification problem expects an expression of this form. It expects neural networks and these formulas, and seeks to build solvers and algorithms that will give you an answer as to whether a condition like this holds or not. So I think a good concrete example, maybe I should have started with this in the first place, is this kind of an ACAS-XU problem. So this is the ACAS-XU sort of benchmark, right? So this is a aircraft collision avoidance system, right? So you have one particular aircraft which is, let's say, being controlled by some neural network driven controller, and it's getting some data from the array of sensors about a potential intruder aircraft, right? So it's getting some data like, let's say, the distance between the two aircrafts, and the velocity of the intruder aircraft, the velocity of my current aircraft, the angle to the intruder, the angle the intruder has towards with respect to my own velocity, and so on and so forth, right? So let's say that it's getting all of these kinds of information, and based on this, the controller is supposed to tell my aircraft whether it should keep going forward, whether it should turn left, or whether it should turn right, and it should give such advisories in a way that no collision ever happens anytime in the future, right? So this is the kind of setting in which we want to look at in the DNN verification situation, and notice that this kind of fits into this previous paradigm very nicely, right? So for example, here one of the things that I might want to make sure that never happens is a situation where the intruder is coming from the right, as I've shown over here, and where I end up also turning towards the right? Because that's clearly something that is going to lead to a collision or lead to a potential unsafe behavior. So that is something that I never want to happen, right? In other words, whenever the intruder is coming from the right, my output should only be either keep going forward or turn towards the left, right? So given this, I can actually encode it in this kind of a form. I can say that, okay, my input is going to be that the intruder is coming from the right, which is going to be some expression involving, let's say, this theta, right? And then my output is going to be it should say that I either keep going forward or turn towards the left, right? And again, I can create this whole expression like this, and then I can you know dispatch it to, like, some kind of an algorithm. And if the algorithm comes out with an answer yes, then it means that at least this particular answer situation doesn't happen, and we have built some trust on the network formally. And if the answer from the algorithm is no, then we have actually found a situation where the network behaves in a potentially unsafe manner, right? Notice here that if my answer to this whole situation is yes, that in fact is going to be true even if the intruder is in a slightly different location, right? So if the intruder was still coming from the right, but let's say slightly below, right? Or slightly, tilted downwards, or maybe slightly further away. In all of these kinds of various slight modifications of the situations, as long as the intruder is towards the right, all of these modifications of the situations are covered. And I know that in none of these situations I ever give out an advisory where I turn towards the intruder, right? So the moment that I have that a property like this holds, the moment that I have a formal guarantee behind it, I've immediately covered a large sort of set of scenarios, and I know that all of those large set of scenarios are going to necessarily be safe for me. Okay. So this is kind of the motivation behind DNN verification, and this is what the problem statement looks like. You're given these DNN n, this condition on the input, which we call the precondition, a condition on the output, which we call the post condition, and you want an algorithm that will give you an answer to a question of this form, right? Okay, so any questions so far? Okay, good. So the rest of the slides are basically just going to talk about some high-level properties of DNNs with the background question in mind as to what is the hardness of this problem. Like, I mean, uh, why do we need such a wide variety of literature to tackle this problem, right? Is it an easy problem? Is it a hard problem? So yeah. Okay, so let's look at some basic properties of a DNN, right? So DNNs is functions. So remember, DNNs are just functions that go from some Rn to Rn, right? So uh, if you consider a DNN as an Rn to Rn function, they have some very nice kind of properties, right? One of the thing is that most of these properties are actually dependent on the activation function. But if the activation function is continuous, then we know that the DNN is going to be continuous as well. If the activation function is differentiable, then we know that the DNN is going to be differentiable as well. In fact, if it's differentiable almost everywhere, the DNN is going to be differentiable almost everywhere. And if the activation function is smooth, then the DNN is going to be smooth as well. Typically, the choice of activation function that we make, as I had said last time, the most typical choice is ReLU. So then, the resulting DNN is at least going to be continuous and differentiable almost everywhere. And this choice is actually tied to how one trains DNNs because one uses gradient descent. And this is the minimum thing you need for gradient descent to work. Therefore, this is usually the case for most DNNs. Um, yeah, there are some interesting exceptions to that, though, which we'll look at. Yeah. So then these are some basic properties of DNS. These can be leveraged during verification, right? So for instance, if I know that I have a counter example, so if I know that if I have an X, right, for which my input condition holds, but the output condition does not hold for this, right? Then I know that there will be some small enough epsilon so that any x plus epsilon will also give me a counter example, right? So counter examples in some sense don't come in isolation, but they'll come as kind of these neighborhoods, and this can be useful in certain situations when we want to handle. So for example, there are a couple of works that utilizes this fact when trying to handle general activation functions. um, Another interesting way in which you can utilize this is that if your output property is simply going to talk about bounds on a particular value, right? So let's say that my phi y simply says that y at particular, let's say y0. So that is the zeroth component of y is just less than equal to 2 or something like that, right? Um, or yeah, so I mean, if it say something like this, then as as long as I can find the maximum value of y, um, sorry, so if I say that something like, let's say that phi y says something like this, that the value of y should not be in this particular interval, right? 0 and 1. So then if I can ever find any value of y that is above 0 and another value of y, above 1, and then another value of y that is below 0, then I know that there will be a value of y that is going to be within this interval, right? Because it's continuous. So you have a y0 that is going to be above 0, above 1, and another y0 that is going to be below 0 for some different values of x, right? So we have some x1 and some x2 which produces these two guys. Then we know that there is going to be some value of x for which in fact this property is going to get violated, right? So these kinds of considerations let us simplify properties a bit, which is again used in a couple of works.
Hmm.
Okay, so yeah, there is another very interesting property that typical DNNs have. which is that the ranges of values for which, typically there are various regions in your neural network where the ranges of values is such that your activation functions become almost linear, right? So if we go back and look at the kind of activation functions that we've been talking about, these are typically things like ReLU, sigmoid, and tan H, right? So I'll quickly just give you a rough graph of these activation functions. This is what ReLU looks like. This is what sigmoid looks like. And then tan H typically is just, tan H is just going to be a shifted version of this at a visual level, right? So notice that you can actually come up with regions here where the behavior of these activation functions are almost linear. This is in fact precisely true for LU. And for sigmoid and tan H, these are just approximations, but you can characterize the degree to which you're approximating these things by considering them as linear, right? So in particular, there are regions or ranges of values for which your activation functions are almost linear, correct? So that means that if I, so remember that my DNN is going to be this, network. And when I say range of values, I'm talking about the value being seen at the intermediate node at some level. And this intermediate node is now coming from a bunch of nodes in the previous layer, right? Which are themselves coming from a bunch of nodes in their previous layer and so on. But nonetheless, if I want the value at this node to be, let's say, within this particular range, there is some condition that will hold on the inputs for which this is actually true, right? I mean, I can, theoretically speaking, construct a condition or a set of conditions on this input for which the value at this particular node will only remain over here. I'm just saying that such a condition, such a region exists, such a set of values exists, right? So then there would be these regions of input where the behavior of this particular node is going to be linear, right? And now you can repeat this for each node in your network, take an intersection. Therefore, there will be regions of input where the behavior of the whole DNN is actually going to be close to linear, right? So you can think of this DNN as behaving almost linearly in a couple of regions with some boundaries between these regions, right? So you have linear regions of behavior separated by boundaries where you have nonlinear behaviors, right? Now, this I'm saying, of course, this is just an approximation for the case of most activation functions. But like I've been saying, for ReLUs, this is precisely the case because ReLU is in fact piecewise linear. So therefore, if you just keep composing piecewise linear functions, you'll get piecewise linear, you'll ultimately get a piecewise linear function, right? So ReLU DNNs are ultimately piecewise linear. But this is also still the case for most other DNNs as well. They're not piecewise linear, but you can find regions in which they're approximately linear, right? So you can find to any degree of linearity that you restrict yourselves to, you'll find some patches in which they're linear, and you'll find a non-linear boundary connecting these patches, right? So at the back of our minds, it's not very it's intuitively very useful to think of these things as being somewhat piecewise linear. Okay, so right. So now I'm going to, given these kind of a background, I'm
Digant,
going to quickly talk about, yeah,
There is some question.
yeah, like I have
yeah,
a doubt. Like, what does it mean? Like, if we fix the like, can you go to the slides? Like, I missed the.
yeah, yeah, yeah,
Yeah. If we
yeah.
fix
Sorry.
the sign of each ReLU neurons, like, I don't get
Hmm.
this line. So, what does it mean? Like, fixing sign of each ReLU neurons?
Right, right, right. So let me maybe yeah, plain instead. Yeah. So what I mean here is something like this. So suppose we have ReLU DNN, right? Um, Let me just maybe take a very precise DNA, right? So these are my input layers. Let's say that we're talking about this particular neuron over here, right? This neuron, if it's a ReLU DNN, remember that this neuron is going to take some weighted, a linear combination of the values in the previous layer, and then it's going to pass it through a ReLU activation function. So what does the ReLU activation function looks like? So let's say that the value going into the ReLU activation function is Z, and these guys are, let's say, x0, x1, x2, right? So what does the ReLU activation function looks like? It looks like something like this, right? So you have 0 when it's 0, and then it's 1, or it's just the input value when it is greater than 0, right? So if I have some values of x0, x1, and x2 such that my resulting z over here is less than 0, right? So then I know that my ReLU is just going to be a constant 0. Similarly, if I have some x1, x2, and x0, so that my resulting z over here is greater than 0, then I know that my ReLU is going to just behave like a, the identity function. In both cases, ReLU is linear, right? So
Yeah.
what is Z though? Z is just some linear combination of x0, x1, and x2, right? So it's some x0 w0 plus x1 w1 plus x2 w2 plus b, right? So this is, if I know that such a condition holds on the input, then I know that my value, the value coming out from this neuron, let's call that z prime, then I know that z prime is always going to be 0. Similarly, if this guy is greater than 0, I know that z prime is always going to be just this expression itself, right?
Yeah.
So this is what I mean by fixing the signs, right? So if I put some conditions on my input so that the sign of this particular the input to this particular node gets fixed, like it's always either positive or always either negative, then this particular node is going to behave linearly, right? So there is some condition I can put here for this particular node so that it behaves linearly, right?
Yeah. Yeah. Got it. Yeah.
Yeah, and I can do the same thing for each of these other nodes. So I have, let's say, so this is my input space. I have some condition for the first node, some other condition for the second node, third condition for the third node, right? And then if all of those conditions simultaneously holds, and if that's actually a feasible region, then what we'll have is this kind of a region where this guy, and this guy, all three of these things behave linearly, right? So the whole network kind of behaves linearly within this region. So therefore, it's kind of piecewise linear. So this makes
Yeah.
sense?
Yeah. Yeah.
Yeah.
Perfect.
Okay. So any other questions on this? Okay, sure. So if there are no other questions, then I'll move into the slides which say why DNN verification is challenging. And I'll cover it from a couple of different perspectives, right? So, of, I mean, there'll be some very high level intuitive perspectives, right? And then I'll go into a bit more formalized perspective, talking about what DNN verifications are in terms of like, you know, in terms of the expressive power. So if DNNs are very expressive functions, then that could be an explanation of why they're challenging. And then I'll go into complexity theoretic result, which says that this is actually going to be NP-hard, right? I didn't want to start with the NP-hard result because that doesn't, for example, stop something like program verification. So program verification is, of course, a very challenging problem, but it has been done to a certain extent, right? So when I say program verification is a very challenging problem, it is in fact undecidable. But it has been done to a certain extent, right? So I mean, you have on a daily basis flights flying almost completely autonomously, and the avionics software inside these flights are written in C. They are running on a computer, and they're doing things flawlessly. And people are trusting their lives on these flights only because these have been through a very formal and rigorous set of safety analysis, which is typically involves verification as well, right? So this is something that has been solved at an industrial scale to a certain degree. Of course, we can't do it for, let's say, very large code bases, but we didn't need to do it for very large code bases in most cases. For code bases that are really safety critical, there is a reasonable amount of effort that one can put to achieve this, right? So is the same thing true for neural networks? No, unfortunately, no. Why? Well, why is it the case that we have been able to do this for program prediction? If it's an undecidable problem, how do we do it in fact in industry? This is something that I think Sir will maybe touch upon a bit when he talks about some of the formal verification techniques. But the intuition is that we understand programs as humans a bit, right? So I mean, somebody wrote code, right? If somebody throws a C program at you, you know that some human being, I mean, maybe now that's no longer true, but you know that at least some human being wrote some program which was used in a training data set of some LLM which generated this at the very least, right? That's the worst case scenario. So you know that there is some amount of reason to believe why there should be a simple explanation as to why this program is correct, right? It's very unlikely that a person will throw a very complicated piece of code at you without there being some simple reason or simple way to look at that code and understand why it works or why it may not work. They have some kind of structure, right? Programs, they have things like loops and branches and so on and so forth. And the structure that the programs have, most well written programs are very carefully maintain this kind of a structure, right? They maintain modularity. You have functions which have very separate concerns, so you can kind of do a divide and conquer kind of a strategy. You verify one function, you characterize exactly what it does in terms of a bunch of formulae, and then you verify another functions, and then you compose those two things, and you can do things of this nature, right? And the idea is that the reason why it works is because there is some underlying logic to it. And in fact, worst case scenario for program verification as well is that you can expect a human to write a proof ultimately for a program, right? I mean, if you are writing, let's say, a program to do bubble sort, and then I ask you, okay, write me a proof of why you think this program is doing something correct. You can write a step-by-step proof, right? I mean, it'll be tedious, it'll take you more time, but in safety critical settings, if that is the time and effort is something that can be spent, right? So it's feasible at least. But that's not true for DNNs, right? I mean, DNNs is, from this perspective, just a black box. We don't know what's going on. Of course, I talked about some of these intuition as to what happens in one layer and then what happens in another layer and then what happens in another layer. But as I said at that point, we don't necessarily see something so neat in practice. We do not, there is nobody who went into the DNNs and adjusted the values of each weights perfectly so that they do something meaningful from a human perspective. We cannot decompose these DNNs nicely into components. Everything is connected to everything. Everything is concerned with everything. Everything is mixed up into everything. There is no modularity, very little structure, no human design, right? And that is, I think, really the challenge behind DNN verification. Um, so there is, of course, a complexity theoretic, perspective as well, but that has not stopped program verification. But it is seen to be limiting DNN verification much more in a much bigger way. And I think the main reason is this kind of black box nature, right? And of
Yeah.
course, I should say that DNN verification is, yeah. Sorry.
Yeah, go ahead. You complete that last bullet, and then I want to add a point. Yeah.
Okay, yeah, sure. And I mean, of course, I want to say that DNN verification is, of course, also just bit new compared to program verification, which has been around for much longer. So maybe it's not fair to make this comparison at this stage. Maybe we'll discover something about networks which will change some of this, but at least this is the current situation for the most part. Yeah, sir, you were saying.
Yeah. See, program verification, okay, there is another reason why DNN or in general machine learning model verification is harder than standard program verification. It's because formal verification relies. I mean, is claims, at least claims that it verifies what a program artifact is supposed to do, what a program is supposed to do. I mean, that can be done only as long as you're able to specify what the expected behavior ought to be. So if it's a factorial program,
Yeah.
it's easy to specify what the expected behavior is. In the case of DNN and machine learning models, what it is supposed to do, because by nature it is not supposed to work precisely, okay? Yet it is it is used and it is assumed to behave reasonably, okay? Now, so formalizing those notions are also hard, and there are various
Yeah.
different kinds of properties that you care about for machine learning models, and DNN, we are speaking about DNN specifically, are somewhat different, okay? And understanding them is, and formalizing them is also adds to the challenge. Okay. No, that is true of program verification too. If you're moving into certain area, and I suppose you want to verify an operating system, okay,
Oh yeah,
then
yeah.
maybe, yeah, what is it supposed to do is thing, and it becomes harder. Yeah. So, but certainly that is quite challenging, the property specification thing for machine learning models. Yeah.
Yeah, yeah. I think that's a very, very good point. In fact, I mean, I'll actually take this opportunity to maybe spend some amount of time on this point as well, because I don't think I've covered it anywhere else in this slide, which I maybe should have. But this is a very nice picture only if you know what these objects are, right? And if these objects looks mysterious, then that is exactly what Sir is referring to over here. Right? This is not, it's not easy to come up with these artifacts. I mean, so this is what we mean when we say specification. The property specification is essentially these things, and coming up with this is in fact hard. Like if I want to say that, oh, my network should classify all cats correctly as cats, how do I come up with a formula that says X is a cat? I mean, that's in fact the problem that we started out to solve in some sense, right? So there are situations where property specification is very, very fundamentally hard. But also there are situations where it's easier simply because of the nature of the problem that the DNN is trying to solve. For example, in this collision avoidance problem, it's relatively easier to specify properties because you know what you should avoid. Like for example, here, what is the DNN supposed to do? It's supposed to avoid collisions, right? That's basically the property, the safety property we want out of it, and that can be specified. So typically, some of these kind of closed loop systems, like collision avoidance, self-driving cars, the property at a very high level at least is kind of easy to specify. But then verification becomes a challenge because now you have a closed loop. You don't just have a DNN, but you have the DNN and a loop, which is much harder, right? So this property specification seems to be a fundamental kind of challenge. But one thing that I would like to say is that there are ways in which you kind of build trust on your DNNs instead of by doing other things than just simply coming up with a property and verifying it. There are other ways of building trust by formally characterizing the behavior, things like explainability. But fundamentally, they still kind of, the way that those problems are solved is by reducing to asking questions of this nature. So that's why I kind of wanted to bring this up. But this is a very good point. Like there are a class of techniques out there which kind of the reason that those techniques make sense is because property specification is hard. Okay, so any questions or anything else?
Yeah, please go ahead. Yeah.
Yeah. Okay. Right. So just a couple of more things, but basically, okay. So what are DNNs in terms of another reason why DNNs are hard, right? Hello, can you hear me? Hello.
Yeah, yeah, we can hear you.
Just a second. I think something is wrong with the audio. Hello, am I audible?
Yes, you are, Diganta.
Okay, sure. So I think my earphones ran out of battery. Yeah. So one of the reasons or one of the cases in which you might want to say that DNNs should be easy to verify is if the DNNs were not expressive, right? So if, for example, if going back to this machine learning parameters function approximator slides, if all that I have is a linear function, right? So if my network is just linear, then it's a fairly simple object, right? It should be fairly simple. It should be a fairly simple question or a fairly simple to answer a query about characterizing the behavior of these things. But of course, DNNs are not that simple, and that's much clear. But how complex are they as a function? What kinds of functions can a DNN be? Well, of course, not any kind of function, because if we restricts ourselves to ReLU DNNs, we know that it needs to be strictly piecewise linear, and of course there are functions that are not strictly piecewise linear. But the interesting thing is that sufficiently complex DNNs can approximate any function. And there's a class of results which says this, which is called these universal approximation theorems, right? So universal approximation theorems are a class of results that are used to describe the expressive power of classes of functions. So polynomials, for example, have universal approximation theorems, but DNNs also have universal approximation theorems, right? So what do they say at a very high level? So there's multiple versions of these universal approximation theorems, but I've got kind of a high level description of two particular results here, just to give you a flavor, which is that for certain kinds of nice activation functions, which are continuously differentiable almost everywhere and not a polynomial, whatever. But for some reasonable assumptions about the activation function, which ReLU satisfies, sigmoid satisfies, tanh satisfies, and so on. If you have any continuous function on a compact subspace, so if you don't know what this means, just think, all your inputs are within some interval 0 to 1, right? So you don't have unbounded inputs. So if you have any continuous function in the compact subspace, this is not exactly what a compact subspace means for Rn, but if you don't know the exact definition, it doesn't matter. Just think on a, given some bounds on your input, and for any degree of approximation, right? So there is a DNN n with one arbitrarily large layer that actually approximates this f up to epsilon. Similarly, there is a DNN n with arbitrarily many layers of some bounded size that again approximates f up to this degree epsilon, right? So if I imagine any complicated function, there is actually a DNN n that will behave very close to this function, right? As close as I want, in fact, right? So then of course it makes sense. Makes some intuitive sense as to why DNN verification would be challenging. Because then if my DNN can really just be any function, then of course characterizing that behavior is going to be challenging, right? But it's still, okay, and I should say that there is, in this next slide, I have precise statements of these things. There's a couple of conditions that I've glossed over here, but I'll not go into those precise statements. But okay, so DNNs can approximate any functions, right? But even then, maybe I need a large number of nodes, right? So for example, I'm saying one arbitrarily large layer. How many nodes do I need? In fact, you'll notice that I'll need a fairly large number of nodes to approximate any f to any good degree epsilon. If you look at the result of this particular approximation theorem, right? So if I anyway need a very large DNN to approximate my function, of course, there are very large DNNs being deployed in the world, but then it might mean that some of the DNNs that I want to verify are actually, representing small or simple functions, right? So what is the relationship between the complexity of the function that the DNN represents and the size of the DNN, right? It might be that my DNN is able to represent arbitrarily complex functions, but we might need proportionately larger than larger DNNs to do that. And then verification should not be easy, because anyway, if you expect me to verify, if you're only expecting me to verify a DNN that you can actually train, then that DNN will only have a certain amount of size. And if size and complexity are always kind of comparable, then that DNN with a certain amount of size, certain bounded size, will have a certain, bounded complexity of the function. So it should be easy to verify, right? So turns out that that is not the case, and this I've already stated. DNNs are complicated, right? In the sense that, this relationship between the complexity of the function the DNN represents and the size of the DNN is actually exponential, right? So yeah, why are they exponential? So two intuitions. I'll give you one intuition and then I'll give you a result rather. So the intuition is, again, let's consider ReLU DNNs, and as we said that it is piecewise linear. So the question is, what is the number of pieces that you have, right? So I'll say that the number of pieces that you can have in a piecewise linear DNN, this is just an intuition. We don't know whether this is always the case. And in fact, knowing whether this is always the case is non-trivial, because it will tie into some, fairly complicated completely theoretic statements. But if we add a neuron to a piecewise linear LUDNN, it can be the case that this now splits a large number of your existing regions into two regions, right? So what do I mean by that? Let's say that I had one ReLU DNA with two neurons previously, and I've got two input nodes and so on and so forth, right? So this neuron can either be positive or negative, and based on the, so let's say this is my space of my inputs, and based on whether this neuron is positive or negative, I can be either on this side or on this side of the line. Similarly, based on whether this neuron is positive or negative, I can be on either side of this line. So now I've got four combination of possible values for each of these neurons. And we know that in each of these regions, each of these neurons will be linear. So therefore, ultimately my DNA is going to be something linear here, something linear here, something linear here, and something linear here, and then connected by some boundaries along these four lines, right? Now, if I go ahead and add a third guy here, it can actually cut across three of these things, right? And now I've split three out of my four things into two new regions, because now to get a linear behavior, I need to fix the sign of this, this, and this. So I need to choose whether this needs to be positive or negative. I need to choose whether this needs to be positive or negative. I need to choose whether this needs to be positive or negative, right? Which means a priori, I mean, this might not always be the case, but a priori, there might be double the number of choices as I had previously, right? And a similar intuition applies to other DNNs as well. The moment you add, like, not just ReLU DNNs, not the fact that ReLU is somehow more complicated, right? Even for things like sigmoid, the moment you add another neuron, you're adding another value, and you have to decide what range that value kinds of lies in to decide whether you're close to 0, close to 1, close to being linear, and so on and so forth, right? So this is sort of formalized in this kind of a proof, which is saying that DNA verification is NP hard, right? Which means what? That we can actually encode, a Boolean circuit within polynomial time into DNA, right? So, and if we can do that, then what does that mean? That means that if you somehow are able to find a very efficient polynomial time algorithm to do verify DNNs, then you should be able to encode a Boolean circuit into a DNN n in polynomial time, and then use your magic polynomial time verification algorithm to find, an answer as to whether this is sat or unsat, right? And then this gives you a polynomial time algorithm for deciding whether the Boolean circuit is satisfiable or not, which would be a big deal, basically, right? And we don't think that such an algorithm exists. So then, it would be reasonable to expect that such a polynomial time algorithm does not exist for verifying neural networks. Okay, so yeah. So this is basically all that I wanted to talk about. I have the SketchUp proof over here, but I think this can be, you guys can take a look at it later on. I think this is, this is all the time that I'll take, basically. So if there are any questions, otherwise maybe we can move on to what Sir wanted to talk about.
Yeah, any questions you have? Yeah, once again, I mean, this kind of leads well into my subject matter that I want to talk about, or at least start talking about. I know it's getting a little bit late there, so I won't take, maybe I'll take about 15 or 20 minutes. See, there are two things. One, Diganta,
Maybe I'll stop sharing, or
yeah, I mean, you could, yeah. So, no, but yeah, even if, yeah, you please, you could.
yeah,
There is he showed that the fundamental complexity in terms as a complexity, computational complexity, that it is hard. There is a methodological complexity, whether that I kind of talked about, and I want to just re-emphasize. Okay, formal verification requires you to specify your expected behavior in some logical language. And so what you want to verify, that behavior has to be amenable for specification in a logical language. And then after that, you need to be able to encode that satisfaction of that behavior by your DNN in a form that Diganta showed earlier in the same logic. That is, I mean, both of them I call as the methodological problem or expressibility. You should need to be able to express that property that you want to verify in that language. So that's also adds to the complexity. And so I think, in my gentle introduction, you should be able to hopefully appreciate that aspect as well. Okay. So let me share. Which one? I keep so many files for my own good. And then, this is the one. Yeah, I'll motivate the, what formal verification is in the context of this particular simple DNN program. Which a DNN example that you already saw and that I showed you how kind of quickly how you could model in the logic of Z3 that we saw last time. And I showed a small proof in Z3 about a property input-output behavior of this DNN. Okay, so let me make this. Yeah, so that example that I showed you is kind of, I mean, exactly. It was here what I have. It says a DNN with one input, and the linear layer has weights 1 and -1, and there's only one hidden layer with 2 nodes. And that is split. The internal node is split into the back node and the front node. The back node takes the the value expressed as a linear combination of the inputs coming into it, multiplied by the weights. And then you take a ReLU, and then you get the forward node represents the value of the ReLU. Okay. And then there is the output layer, which is once again a linear combination of these the values at the forward node. Now, and what you see on the right side box is what I typed in my last class into Z3, saying, and what I wanted to verify was that as long as VNN V11, I think was, I guess in this case, this is slightly different than the one that I tried to verify last time. So there is no ReLU at the output. And actually, there is no output there. This is what the expected behavior is. I mean, in this case, it was simple to specify. Okay, and so the last line here is the expected behavior, and all the other lines, what I define as DNN, the function DNN, the other lines, the formula that is shown here is supposed to characterize on these lines here are supposed to characterize the input-output function represented or defined by the DNA. Okay. So, and before I ask you the question, why indeed, one question I have that I'm going to ask you is why this formula indeed represents the function implemented, defined by the DNN. Let me list formal, informal verification. There are actually three important steps. Okay. One is you have to model the behavior of the artifact, that is the design, the artifact under verification as a formula. In this case, it's a neural network. And so we have to modify the function that is defined, the input-output function that is defined by the DNN. And so that is the first step. The other thing is you have to model the expected outcome or behavior as a formula in the logic, and that's what a property is. Then you check that you construct another formula, which is usually called a verification condition, which, when valid, there are various ways to express, when valid, it's guaranteed that the model satisfies the property for all scenarios. And that can be, in this case, expressed as this one. So DNN is, once again, a formula which characterizes the function, the input-output function, and then it will be expressed as whenever that function, relates its input to its output in a way that is characterized by the formula defined as a DNN. It is always the case that the property, the formula that characterizes the property will be true. And that's what you want to be valid. Why valid? Because you want to show, in our case, the properties, I wanted to show that once the DNN is trained and on all test data, that it behaves as specified by the formula prop. Okay. And that is a validity property because you want something to hold for all possible values that the variables involved in that in the formula can take. And therefore, that is expressed as a validity. The check is a validity check, which when you do in SAT solver will be converted into a checking the unsatisfiability of the negation of that formula. Okay, so that means this formula that I've shown here. Okay, so now, is there any questions? So these are the three steps. One is modeling the behavior as a formula, modeling the expected expected property, the property that you want to the model to satisfy, and expressing the satisfaction as that as a check in your and as a verification condition that needs to be checked. Now, given that, first question that I'm asking is why this formula that I've written here characterizes the function. In what way does it define precisely the input-output behavior of the DNN on the left side? Can anyone tell me in what way? So do you believe that this the lines, okay, the DNN function defined by this formula, in what way and why do you believe that it characterizes the function defined by the DNN?
For every node we are trying to like in a single node, if the sign is equal, like we are trying to see if they are equal. So for every node, or like kind of using modularity for of each nodes, and then comparing this to the output,
Yeah,
kind
I
of
think
thing.
that's yes, that's a good point. Yes. So firstly, there is a logical variable here corresponding to that denotes the value at each layer, within hidden layer being split into these two. So V21, there's V11, which models what the input is, V21B, and so on. And yes, that's first. So the meaning of the variables, okay, is exactly corresponds to the values that are produced at these at various nodes in the input layer. That's the point. That I guess this was Aritra. Who was that?
Yeah, Aditya.
Yeah. And secondly, this, and I guess you also made that point. So each of the conjunct here defines the value, okay, of of the value of that variable in terms of the previous the variables denoting the nodes at the previous layer, okay. So, for example, V21B, this equation defines that. V22B defines the value of V, for at that node before the ReLU, and the ReLU behavior itself is defined as a conjunction of two things, as a conditional, okay? The case when it is less than zero, and the value at V21B is less than zero and is greater than or equal to zero, okay? And so on. And there is another way. So in that sense, since it captures each of these equations, and captures the value precisely, and all that is put together in a conjunction. So all of them have to be true simultaneously. So that is the way that in a sense it is done. But there is a higher level at which one can say that this behavior is exactly captures the other one. Every time for any value of these variables, V11 here, there are how many variables involved? 1, 2, 3, 4, 5. There are 6 logical variables involved in defining the formula. So whenever for every pair of values that V11 and V31 can take, that makes this formula, this big conjunction shown here, true. Okay, so for every satisfiable instance of the formula that is shown here, for every pair that makes V11 and V31, that makes this true, exactly, corresponds to a situation where that particular V11 is mapped to the output V31, okay? And that is what is the essence of this formula is. And the way that it is constructed makes the observation that I made to be true. And that's the reason now you're able to express your verification condition as a validity. So whenever you have, for every pair of input-output pair of values that are legally produced by the DNN, then that the property, which presumably in this case is relates V11 and V31 in the last line that I've shown here should hold, okay? And that's what the condition expresses, okay? So in that sense, this is a sound way of characterizing that verification problem. Of course, this is, as your machine learning model gets more complicated, or then there may be different ways in which you can make the model, and how you model may get more complicated, and different modeling techniques may produce the size of your encoding may also change depending upon what methods you use. And similarly, depending upon what property you want to verify, your property may not be expressible as simply as an equation. All that. So there is encoding of the behavior, encoding of the property, as well as encoding your verification condition. All of that can change, and those are some specific things that one has to come up with as you implement this concept to real machine learning models. Okay, so now what I want to do is to express. Now, since I said I'll be introducing you to program verification, and how exactly did I derive this itself can be viewed in terms of how you would apply this to a program. Okay, here I directly derived the formula that modeled the behavior. Okay, since going layer by layer. Let's take a slightly different method here. So here, this DNN is expressed as a program. You can view this DNN as, you can define it, implement it as a sequential program, which is what I've done here, okay? So V21B, it's a sequence of assignment statements, some of which are conditional assignment statements. So, for example, V21B is equal to V11, okay? I mean, it takes the same values, V1, and then V22B is minus V11, and so on. So, the V21F can then be, implemented as a conditional statement, and similarly V22F. And finally, V31 is implemented as an assignment statement, which assigns the linear combination of V21 and V22F, okay? And as a matter of fact, the formula, so now you can express this, what we try to prove here as proving the pre and post in the form that Diganta stated earlier in his lecture. So the pre here gives the condition under which you want to the assumption under which you want to express the property. I mean, the property here has, assuming that the input satisfies certain condition, the output should satisfy the output value should satisfy certain condition. And here I have modeled the DNN as a sequence of assignment statements. Okay, so now, how do you then prove the? Then the question is, how do you model the behavior? The question will be, how do you model the behavior of each of these individual assignment statements when this is viewed as a sequence of assignment statements as the program implementing the DNN? Okay. So, we can ask that question. Okay. As a matter of fact, viewed as a program, DNN is quite restricted. You will see that in that sense, program verification, in that sense, at least the modeling of your modeling DNN as a program can be done using a fairly restricted program, because every variable is assigned at most once in here. Unlike in your traditional program, you can have variables being assigned multiple times. Okay, so every variable here is assigned at most once, and the program has branches but no loops. Okay, at least for this kind of DNN, there are no loops. So in that sense, DNN is quite restricted. Okay. Yes. So in terms of, methodological thing, when you look at the techniques that are, if you want to leverage techniques from program verification to DNN verification, because of these restrictions, you might, in some sense, the the verification techniques can be simpler. Okay, so I'm kind of contradicting what Diganta in some sense said. He looked at the complexity of verification of the function implemented, but here my statement is on the methodological side. Okay, so if you want to apply software verification techniques, once you know the property that you want to verify for DNN, some of those techniques that you need are very easily amenable, the program verification techniques. So in that sense, it could be simpler, but the problem itself, the complexity of the problem itself, can still be very hard, like Diganta pointed out. Okay, um, so now, viewed as a program, the DNN, let's see how we can go about, another way I'm showing, okay, of how you could verify this thing. So this also, I'm pointing out why, another point that Diganta made, okay. So once you express it, the DNN as a program, you can leverage the structure of that program. So in program verification, that modularity, there is a structure in the way that these programs are built, which can actually be leveraged, and that makes it easier to apply logical techniques to program verification, which is not the case when you view DNN as complete black boxes. Okay, but here I'm kind of opening up in order to actually motivate program verification. Okay, so now that we have started using that example and expressed it as a program, let's see how we would go about verifying this DNN implemented as a sequential program. Okay, so and this program verification, the whole thing started out as by people defining special kind of logic, okay, to verify that are suited for verifying program behaviors, for asserting program behaviors, and that's what I'm introducing here. Specifically, I'm introducing the notion of strongest post condition. Okay, so assuming that this precondition holds good, say a pre defined by pre, that pre is a condition. It is a condition that holds good, that characterizes what your inputs space is. So here I'm asserting that V11 has to be negative. Okay, so now you can ask the question: what is the predicate or the formula characterized as a formula that should hold good after you make this assignment? What is the strongest thing that you could state after this assignment is made. Okay, given that VA11 is strictly negative before this assignment statement is executed, what can I say? What can I say about what the state of affairs should be after the assignment is made? Okay, can anyone guess? Can anyone tell me what does this assignment do? This assignment makes the value of V21B to be the same as V11, correct? So given that as the meaning of this, what is the strongest thing that you can state about V21B and V11, which are the variables that are of concern here? You can be sure that V11 should be equal to V21B, correct?
Yes, sir.
Yeah, so if that is the case, ignore the X here, that's a typo, then since you know something about V11 itself, you could then, the strongest thing that you can say about, thing that here is that V21B is also negative, correct? So because you know that after this assignment, V11 will be equal to V21B, and therefore what you can state here, once again expressed as a formula representing a predicate, you could derive that V21B should be a negative as after this assignment. Similarly, V22B is minus V11. So based on the way that the program assignment semantics works, you know that V22B is the negation of V11, and therefore here you could conclude that V22B should be greater than or greater than or equal to, you can actually conclude that it is greater than 0. Okay, and so on. Similarly, if after you do this assignment statement, the assignment statement works in two parts. One is under the condition that the Boolean expression is true. Then you make some assignment. You assign V21F to be 0, and V2 that if in the other case you assign make V21B to be the same, V21F to be the same as V21B. So under the same thing, now you could come up with similar conditions that ought to hold good after the execution of each of these two arms of if then else. And then as a result of executing this entire statement, both the arms, now you can once again construct what the predicate that characterizes what the state of the values of all the variables ought to be after this conditional assignment is made, and that's what is characterized by this formula. Okay, so here it states that if V21B, I mean, you can assume that P2 holds good, assuming that P2 holds good prior to the execution of the statement. And in that state, if V21B is less than 0, then you would have P2 prime, okay, of V21B is greater than, is not less, is greater than or equal to 0, then something else holds good, which is two assignment statements, and then you can derive them, and so on. So in this way, you can propagate all the values forward until you get to a precise statement of the state of affairs at the exit point of your program. And then you can then use that predicate to show if your expected post condition is holds or not. Kind of this is the basis, okay, for doing the thing. So steps involved in the program verification, you start with a pre. Is a predicate that specifies the set of permissible states at the entry point of the program. Then, and this is the specification part, okay? The post is a predicate that specifies the set of all expected states at exit. That is your property that you want to verify as a result of executing the program. Then, and the way that you model your program is by constructing the strongest post condition after every statement. And that is you have to that is given by this schema, okay? Strongest post condition for each predicate that holds, it describes the state of affairs at the beginning of the execution of the statement. It produces, defines the predicate that defines exactly the set of states possible after executing. And then you could do this step by step until you get the strongest post condition that ought to hold good at the exit point, and then you show that indeed implies your expected post condition. And this is how program, and this whole thing, the way that I did it, can be expressed in a calculus and can be calculated in an automatic mechanical fashion. Okay. And so I just wanted to contrast these two things, and we will look at more about how to define this SP for a small programming language, so that gives you an idea when I continue the lecture next time, okay, in the next class. And what happened in here was when I constructed the model here as a formula, you did it in a more directly, okay, by relying on an informal behavior of how DNN ought to was going to behave, and then I constructed it directly, and you see that the basis for the way that I derived the formula as for characterizing the behavior was somewhat similar to the way that the strongest post condition were constructed when you view that as a program. Okay, so and that's the contrast that I wanted to bring out here. Okay. Okay, any questions here? I think this is a good point for me to stop. Do you have any questions? Okay. In that case, I'll see you next week, and we'll continue this discussion.